This section of work is about the continuous uniform distribution, or the rectangular distribution. And the probability density function looks like this. You can see that the probabilities, or the probability remains constant between two numbers. The lowest possible number and the highest possible number, alpha and beta, are often used. So there is no change to the probability of any event happening. It's a constant probability. Clearly, as with any probability density function, the total area has to be 1. And the width, as you can see, is beta minus alpha. So because the total area is 1 and the width is beta minus alpha, then beta minus alpha multiplied by the height has to equal 1. So the height is 1 over beta minus alpha. So the probability density function is 1 over beta minus alpha when x is between alpha and beta, and it's 0 otherwise. Now the mean is clearly, by symmetry, halfway between alpha and beta. So the mean is alpha plus beta. And because it's symmetrical, then the median is also a half alpha plus beta. And there is no mode, because every number is equally likely. Every number between alpha and beta is equally likely. Now you could get asked to prove that the mean is a half beta plus alpha. So this is the proof, and you need to know this. Obviously the mean for any probability density function is x f of x, and that's between the two. And so between the two limits of alpha and beta, we get x over beta minus alpha, because f of x is 1 over beta minus alpha. So if you integrate this, we get a half x squared over beta minus alpha between alpha and beta. And then we have to substitute in the values, so we get a half beta squared over beta minus alpha minus a half alpha squared over beta minus alpha. So a half is a factor, and then beta squared minus alpha squared is beta plus alpha over beta minus alpha. So we can write that as a half beta minus alpha over beta plus alpha, because that's beta squared minus alpha squared, and then the beta minus alphas cancel out, and we get a half beta plus alpha. Now, although this formula is in the formula book, you could possibly get asked to prove it. The proof of this is in the syllabus, so you need to know this. So I can hear you asking, what about the variance? So the variance of x is the expected value of x squared minus the expected value of x all squared. So we need to work out the expected value of x squared first. The expected value of x squared is x squared f of x dx between the limits. So that's between alpha and beta. It's x squared over beta minus alpha, because that's what the probability density function is. So then we need to integrate this. So that's 1/3 x cubed over beta minus alpha between the limits alpha and beta. So let's substitute those in. So that's 1/3 beta cubed minus 1/3 alpha cubed over beta minus alpha. A third is obviously a factor, so we get beta cubed minus alpha cubed over 3 beta minus alpha. Now we can do this exactly. Beta cubed minus alpha cubed equals beta minus alpha, and then see what we need to multiply by to make this correct. So beta times beta squared is beta cubed, but that gives minus alpha beta squared. We haven't got any alpha beta squared, so on this bit here we need to have an alpha beta. so that we get plus beta squared alpha. But that gives us minus beta alpha squared, so we must have here a plus alpha squared to give us plus alpha squared beta. And then as a check, we've got our minus alpha cubed. So altogether, so let's just put this in a bracket and carry on with our proof. Beta cubed minus alpha cubed over beta minus alpha, we can see it's this divided by this, which leaves us that. So that's beta squared plus alpha beta plus alpha squared all over 3. So now we know what the expected value of x squared is, we can work out what the variance is. The variance is the expected value of x cubed x squared minus the expected value of x all squared, and the expected value of x we have as a half beta plus alpha, so it's a half beta plus alpha all squared. So this works out to be 1/3 of beta squared plus beta alpha plus alpha squared minus 1/4 beta squared plus 2 beta alpha plus alpha squared. So let's take 1/12 out. So if I've taken a 12th out and this was a third, I've got to times everything here by 4. So it's 4 beta squared plus 4 beta alpha plus 4 alpha squared. But I've taken a 12th out, so I've got to times everything here by 3. So that's minus, everything's minus, so it's 3 beta squared minus 6 beta alpha minus 3 alpha squared. So it's 1/12. 4 beta squared minus 3 beta squared is 1 beta squared. 4 beta alpha minus 6 beta alpha is minus 2 beta alpha, and 4 alpha squared minus 3 alpha squared is alpha squared. Now this is beta minus alpha all squared. So this is 1/12 beta minus alpha all squared. Now, as before, this formula is in the formula book, but you could just possibly get asked to prove it. So that's why you need to make a note of this proof. Now we need to consider the cumulative distribution function for a continuous uniform distribution. And the cumulative distribution is the probability that x is any number up to a particular point. In other words, we need to find out this area. So we need to find out this area in terms of x. So the area is simply the base length times the height, because that's the area of a rectangle. So the width is clearly x minus alpha, and the height, we did that before, we worked out the formula for the probability density function, and we got 1 over beta minus alpha. So the cumulative distribution function is 0 when x is less than alpha. It's the base times the height, so that's x minus alpha over beta minus alpha when x is between alpha and beta, and it's 1 when x is greater than beta. So this is the cumulative distribution function. So here's an example. We've got a continuous random variable. It's uniformly distributed on the interval 1.25 to 1.35. So it's going to look a bit like this, with 0 there and 0 there. So the mean is a half alpha plus beta. So that's a half of 1.25 plus 1.35, which works out to be 1.3. And the variance is 1/12 beta minus alpha all squared. So that's 1/12. 1.35 minus 1.25 is 0.1. So it's a 12th of 0.1 squared, works out to be 1 over 1200. So that's simply using these formulas that we've just derived. Here's a second example. This time we're not told what alpha and beta is, but we're told that the mean is 14, so alpha plus beta over 2 is 14. In other words, alpha plus beta equals 28. And we're told the standard deviation is the square root of 3, so the variance must be 3. The variance is the square of the standard deviation. Don't forget to use the correct formula. It's a 12th beta minus alpha all squared. So that means that beta minus alpha all squared is 36, which means beta minus alpha equals 6. So we've got two simultaneous equations. Let's call them 1 and 2. Let's add them together. And we get 2 beta equals 34, which means beta equals 17. Substitute back into the either 1 or 2, and alpha works out to be 11. So what we've got now, we can see, is a uniform distribution, continuous uniform distribution, going from 11 to 17. We want the probability that x is less than or equal to 12. So what we want to know is, let's just make it clear what's happening here, there we go. So what we want is this area here, where this number here is 12. So because the width is 6, the height must be 1/6. Remember, base times height is area, total area is 1. So the height is 1/6. So this area, which is the probability that x is less than or equal to 12, is equal to the base times the height, so that's 1 times the 6th, which is 1/6. So here's the third example. We've got a channel tunnel with access every 375 metres. The train's broken down, needs to be evacuated. What's the probability density function of the distance from the nearest access tunnel? So assuming that it's equally likely that the train breaks down at any single point between these access tunnels, we can use a continuous uniform distribution. So what's alpha and what's beta? Well, if the passengers are really lucky, it breaks down exactly at an access tunnel, so the smallest distance it could be from the access tunnel is 0. The greatest distance is when it's exactly halfway between the two. 375 divided by 2 is 187.5. So the greatest distance from any access tunnel, either walking backwards from the last one or forwards to the next one, is 187.5. So our continuous uniform distribution looks a bit like this, where this number here is 0, obviously, and this number here is 187.5. So the probability density function is going to be given by the height of this. So because that length here is 187.5, and because the total area is 1, then the height is going to be 1 over 187.5. And you can simplify that to make that 2 over 375. And this is when x is between 0 and 175.2. But otherwise it's 0. So it's 0 otherwise. It's 0 there, and it's 0 there. Now the upper quartile of x is going to be given by the point here, where this area here is 0.75. So we need to find this point here, which is Q3. And clearly Q3 is 3/4 of 187.5. Which works out to be 141 to 3 sig figs. Obviously this only works because it's a uniform distribution. If this was going up or down or curving, then it wouldn't be quite so straightforward. But because it's a uniform distribution, then this length here is 3/4 of the whole length, because the area is 3/4 of the whole area.